Hi, I'm Harry Saal, President of Network General, and I thought I'd spend a little time and have you look over my shoulder, so to speak, at some of the more interesting examples of network traffic that we've found looking at actual customer networks. And in particular, what I'd like to do is to share some of the ideas and ways that we've found are useful in looking at these traces and trying to notice that things are not really the way they should be. Trying to spot patterns, to spot situations that just look strange or odd without really necessarily having to be an expert on the protocols to look for those things that stand out in a fairly obvious way once you're looking for anomalies. How to identify them, how to focus in on them, and I hope by the end of this session you'll have some idea yourself of what you might look for when you simply turn a sniffer on a network that otherwise has really not been screened and cleaned and tuned and honed and preened. What you're probably going to find difficult to accept is that the examples I'm going to give you are really very typical. They're things that are frankly easy to find. Virtually every single network has problems. Sometimes, I will admit, they're a little harder to dig out. They don't leap out at you. The examples here are perhaps brazen, bold, obvious. I hope they'll be obvious to all of us after the session. But nonetheless, virtually every network we've looked at has problems just about as gross as this, and we ain't seen everything yet. So perhaps we'll be putting together another tape and show you some more examples of the kind of things that happen on a network. Now, the examples we've chosen for today come from a variety of different network protocols. They include examples of problems, typical problems that you might find on a TCP/IP network, problems on DEC networks, problems on Novell networks. And we wouldn't want to particularly pick out these networks as being more or less susceptible to these problems, but they're quite standard. These are probably the three most popular networks that you'll run into in an Ethernet environment. The examples are taken from Ethernet, again, using that just by way of reference, since that is probably the most common network you're likely to run into in your analysis. So let's begin. What we'll do is for the first example, we will actually play back the trace using the sniffer's replay capability and see if you can just get an idea from the capture screen that looking at the source and destination addresses that there might be something here worthwhile. What I'm going to do is to set up the unit so that instead of capturing from an actual network, I will select a particular file. Normally we'd leave the sniffer on capturing from actual Ethernet network. In this case, rather than that, I'll just select a file, this one called ARP Blast. This is a good way to take another look at the dynamics of a network. One can often see different things if you're looking at it in pair count mode or skyline mode. In this case, we'll be looking at it in pair count mode. I'll press F10, play back the data. It's a very short trace here. We only have 150 frames. It lasted 1 second. And something really unusual stands out in that 1 second of activity. There was a burst of activity. I'll play it back again. The screen suddenly half fills. The rest of the screen fills. In fact, that means we have more than some 40 stations in a period of time of less than a second. That in itself is very unusual, that you would have that many stations transmitting on a network within any one given second. A good way to look at that, by the way, is as data is coming in, I'll play back this trace again, keep it playing back over and over again. If I press the F4 key, okay, I can clear the screen. And generally, in a standard case, if you clear the screen, you would see a few stations. Addresses will come back. 2, 5, 10, 20. Not a blast of station addresses like that. Right away, that's a clue that something unusual is going on here. There's something a bit more unusual. In fact, if you notice, the source destination of all of these stations is broadcast. Again, fairly unusual. We might see a network which is very active, stations transmitting back and forth. Again, you would not expect to see a network filled with broadcast traffic with several hundred frames of broadcast traffic in a matter of seconds. Well, of course, we've isolated just this particular section. If we were looking at the actual network, in fact, there was a burst like this, and then this was followed by some normal activity. Here we have just a short period of 1 second, and I'll load that data back, and this time we'll actually display it. And here we can see the actual traffic on the network, frame by frame, being decoded. And what do we see? Several things. Again, stations are broadcasting. An observation we can make very quickly: we didn't know anything about the particular stations here. The first station happened to be a board whose manufacturer was Micom Interland. These other stations all were apparently made by Sun Microsystems. And just looking at the summary screen here, I noticed that the summary line appears to be virtually identical in each of these. It's an ARP, address recognition protocol, command. The letter C is a command. And basically what it's doing is saying, gee, I'm looking to find a station whose internetwork or IP address is 128.18.4.0 and who speaks the protocol IP, internetwork protocol. And suddenly, a whole bunch of stations here all are broadcasting requests to locate that particular station. Again, this is very atypical to see any kind of really serious repetitious behavior like this going on. To make it even clearer what's going on is take a look at the left-hand column where we see delta T. If you look at delta T, you'll notice the times between these frames here. This is 3 10,000ths of a second, 1 10,000th of a second, 0. It's even less than the resolution which is displayed by the sniffer. By the way, the sniffer is keeping the data roughly 10 times more accurately than this. We've chosen to display the information since normally things happen in millisecond times or hundredths of millisecond times. Generally, we round up the data to a tenth of a millisecond. That's what this packet 4 is, approximately a tenth of a millisecond. Packet 5 came even less than a tenth of a millisecond later. Packet 6 as well, 2/10 of a millisecond later. This is incredible traffic. These packets are virtually back-to-back by their arrival times. Now, they would have to be spaced out somewhat farther. They would have to be spaced out somewhat farther if they were larger packets. Here, notice there's a pause of 1 second. There's no station activity for 1 second, and then in fact these stations, these are the same stations again, send out their request for this ARP. That's when you see a pattern like that, again, probably what we're looking at is a retransmission. I would just guess the reason for the 1 second delay is that all these stations up to packet 20 sent out a request. Nothing happened. Between packet 19 and 20, there was no activity on the network. These stations are still waiting for someone to reply to these ARPs here prior to station 20, and they try all over again. And they're going to do that several times in a row until a reply happens. Let's look down forward here. This network is, these packets are so close together, by the way. I should mention that when packets are that close together, they generally will induce deafness in the receiver. Anytime you see packets being transmitted to any one station by address, or in this case, even worse, broadcast, which means that every single station on this network, which by the way was several hundred stations, every station receives this packet into its buffers, into its hardware, and literally, like you would, goes deaf because it can only handle a few broadcasts close together or a few messages sent to it close together in the best performing hardware. So you can guarantee that at this point, virtually every station on this network is deaf, is missing packets, is losing things. This is going to cause hell to pay downstream after this explosion happens. And eventually here, by the way, you can now notice here these ARP followed by the letter R. That's an ARP reply. This is presumably some station identifying himself, responding to all these commands that we saw, saying, here I am, I'm the station you're looking for, and here is my physical address, which is over here in this protocol. It says hardware address equals 0207010035D1. Curious thing, notice what's happening here. Here are a whole bunch of ARP requests that are going out. Each of those requests is trying to find a station whose inter-network address, whose protocol address, is 128.18.40. The normal thing you would see as a reply is a station replying to that saying, hello, my address is 128.18.40, and by the way, my hardware address is such and such. What's really unusual in this case is, in fact, that these replies down here, which are all coming from this board made by MICOM, in fact have a different protocol address. They do not have the protocol address that's being looked for in the ARP. That is probably incorrect implementation of ARP, and these stations will ignore those replies, and each one of these stations is now getting a packet back from this MICOM board. We don't know who the manufacturer of the software is, with an ARP reply that really is inappropriate to the ARP request that was going out. So one thing we notice is probably we should look and see whose software was running on that board and take a look at why it was replying in the way it is. Now let's go back. I'll press the home key. We'll look at the first packet. What caused this whole situation to occur in the first place? This is an RWHO packet, a remote WHO packet. It's Unix. I'll turn on a detail window. And here we see in the detail window, this is a remote WHO frame. This is a frame which is typically broadcast every 30 seconds to a minute by Unix systems in the standard configuration. And it contains information as to who's logged on to this Unix system. And it's used to inform other systems as to how busy these stations are and so on. This particular case, it's telling us that nobody was logged on. And if we look here at this line, in fact, in the last 5 minutes, 10 minutes, and 15 minutes, there's been virtually no utilization of the CPU, 0.00 utilization. So not a hell of a lot's going on, and this station is informing everybody else that not a hell of a lot's going on. Let's go up and look at the hardware level. This is a broadcast packet that was being sent out. That means every station on this network is going to receive it into its hardware buffers. And if we look at the inter-network protocol, what we find is that this station, this packet is being broadcast to stations 128.18.4.0. Now that's not a broadcast address. That is a specific address of a station on this subnetwork that it's being broadcast to. And what's happened is that each of these other stations has picked up this address and decided that it would like to forward this packet. If you look at the last digit of this address, you'll see that it ends in 0. Internetwork addresses that end in 0 or 255, depending on when you were born, may or may not be broadcast address. One of the great confusions in TCP/IP historically has been whether or not addresses that are meant to be broadcast should end in a 0 or end in 255 or end in 2 zeros or 255. Presumably what's happening here is this station has decided that he'd like to broadcast this to all those stations on the subnetwork 128.18.4, and the 0 means at most the 255 stations on this network. That itself is a reasonably safe thing to do. Unfortunately, what happens is that every other station on this network, and these are all these ARP replies that we're looking at, gets this packet, and they're using an older version of TCP/IP software, which thinks that station 128.18.4.0 is a real station, and this packet is destined for that specific station, and they're going out trying to find out how they can forward this packet to that particular station. So they send out a request using the address recognition protocol saying, gee, is there anyone out there who has the particular address 128.18.40. In fact, there is no one with that address. That's a limited form of broadcast. But all these, literally some 20 or 30 stations, decide to broadcast that. Again, we can see that happening. You can argue back and forth in a case like this, who's wrong and who's right. You're never going to win it. This is a classic situation where software has changed historically, and probably different versions of software are running on the Unix machine in packet 1 and the other Sun machines on packets 2 and so on. And one has to go in and modify the software, upgrade it to deal with the particular form of broadcast that's happening. In the meantime, the effect of this is, and what was reported by the user was, periodically, once every half hour or so, which is curiously about how often these RWHO broadcasts are sent, all kinds of file transfers stop working, terminal sessions stop working, and basically the net effect of all these broadcasts and retransmissions and multiple ARPs is to cause all kinds of other connections in this network to basically break and time out. Nothing's broken with the network, but someone's going to have to go and modify. Presumably the simplest thing to do is to change the software running on this Unix machine to no longer broadcast the RWHOs. That's not a very important practice, and that could just be stopped by editing a configuration file, or it could be changed from once every half hour to once every day, and everything else would come back to normal on the network. So, the next example that we'll look at is one of a DECnet system. So load this file called decroute. Perhaps first what I'll do is actually, let's play back the file, so we can get an idea of how many stations are on this network. I'll make this the source of capture. And for example, if I use the option individual counts, that's a quick way of finding out how many stations are actually transmitting during the session that we're looking at. So I'll now press F10, play back the file. We can see there are about 25 to 30 stations on this particular Ethernet segment. They all happen to be running DECnet Phase 4, which is the most recently shipped version of DECnet. The system has substituted the letters DECnet in the upper half of the address since it's recognized the particular addresses that DEC uses. Now let's take a look at the actual frames themselves. Turn off the detail window. We'll just look at the summary window here. Let's make some observations about this DEC system. Notice the first few frames here are what are called end-node hellos. An end-node hello is information about the particular configuration of that station on the DECnet. It's providing its address. This is DEC's form of addressing here. For example, this one is station 2.3, which is area 2, station number 3. Areas are typically separated geographically. An area might be a city or a different building perhaps, and substations would be the individual stations within an area. Stations within one area are connected together by what DEC calls level 1 routers. Back down here you see there's information from the DECnet routing protocol about level 1 routing information. And then the level 1 groups are connected together usually by slow lines that go from city to city. Those are called level 2 routers. All the routing is done within a level 1 area by level 1 routers, and then there's one level 2 router which is meant to take data from one level 1 area to another level 1 area. So here we see these end node hellos. One thing you'll notice right away is here what it's showing us is the block size, that is the maximum packet size that these particular end nodes will receive or transmit. Right away you'll notice that this station, 1.2, seems to be set with its maximum block size at 576 bytes. These other stations are using block size of 1498 bytes. The maximum size Ethernet packet is around 1514 bytes, less overhead and whatnot. 1498 is as close to the edge as you can get with DECnet. This station here apparently is configured to use a smaller block size, a block size that might be reasonable for a wide area network, but in fact it's going to end up that in such a way that transmissions to and from this station will use multiple Ethernet packets instead of a single Ethernet packet because of the way that station is configured. It's a simple thing to change. Notice down here, station 1.6 also, 1.60 also has block size 576. In this case, this is a router which is identifying itself as opposed to an end node. 1.6, of course, is a router. It'll also show up as an end node. Let me show you how we might look if we wanted to go back and check just end node hellos. Let's put on an end node hello filter. Understand how we'd look at that and check whether or not there are any others that have a block size other than 1498. To do that, we'll turn on a detail window and a hex window. We'll put our cursor in the detail window. Notice here, this byte, control packet format 0D, apparently means these bits here indicate that this is an Ethernet end node hello message, and it's a control packet. So, simple thing to do is, let's just filter on all packets that have this particular byte there. That'll get us to a set of packets which is probably pretty close to just the end node hellos. So to do that, we'll just go to our filters, put on our pattern match filters, and for a pattern, since I've pointed to the byte in question, I'll just use the up arrow to copy that byte value into the pattern. I'll use the same trick in offset. I've pointed to it in the detail window. I'll use an up arrow to copy its offset. And now I'll just press F3. And let me now put the cursor in the summary window, press F4 to zoom out. And it looks like, in fact, we did pretty well. We happened to catch things that look pretty much just like end node hellos. Now we can see there are several of them here. I'll hit home that are 576 is station 1.5. Here's station 1.5 again. Okay, we could again set up a filter if we like to look at just these. That's one thing we might like to clean up. I'm going to go back to my filters and turn off that filter. One way to do that is just to press spacebar here and disable the match to filter. Now if I go back and press F3, I see all of my data again. Now, what's interesting here, a couple things. We have some router information. We'll come back to that. There's a level 1 router. Here is some NSP data. That's basically data transmission that's going to and from two DEC nodes. The first thing we see is begin end. Someone's sending data, then an acknowledgement. Begin end, he's sending another data packet, acknowledging it, and so on. Out here, if I look all the way to the right, I can see the length of the data. If you could zoom in on this. Here you can see this first packet happens to have 15 bytes of data. Another packet has 15 bytes of data. Notice, in fact, by these data segment numbers, these are not successive packets in that same transmission, whereas these probably are. Without even looking at the source and destination, this 161 bytes and this 26 bytes, this is data segment number 3425, this is data segment number 3426. Those are probably sequential packets that are being sent, and we can check that by looking at the source and destination to and from the same guides. Let me just continue to look down here. Notice here again is data segment 161, length of 161, length 26, data segment 3515, 3516. Notice here length 15, length 15. Exercise for the reader, we won't talk about it here, but I find it somewhat remarkable to just happen to see this pattern of 161 followed by 26 here, 161 followed by 26 here. These are coming to and from different stations. But my sniffer antenna goes up when I see things like that, and there are a few more examples in this trace that you might look for. And I wonder whether or not, in fact, what we're seeing here is the same data being transferred between two stations in a kind of a store and forward pattern, and then being transmitted from those two stations, from that intermediate station to some other station. And this is something we look at by then looking at the specific DECnet addresses of these packets and so on to see whether or not this data is in fact being transmitted twice on the same Ethernet. Okay, well, let's imagine though that we don't want to focus on the data transmission. We want to look just at the routing information. So what I'll do is turn on a filter, and I'll pick DRP for DECnet Routing Protocol, turn off all of the protocol filters, and then turn on just DRP. Notice here is the information we're looking at. Gee, I can't resist the temptation. This is how we find out these things. This section of data that we're looking at here is the NSP transport data that we're looking at. And what I just noticed is that, in fact, the source and destination for all these packets is actually from source area 1, station 86, destination area 1, 88. And in fact, I suspect that these packets are retransmissions. Here's how we can find that out. We'll go back now. I'll turn on, in addition to DRP, NSP. There's NSP. Turn that on. In this case, I can go to my summary window, turn off highest level only, so I'll see both NSP and DRP. And here what I can see is, for instance, that this packet, which is length 161, okay, the preceding line is the DRP showing me that it's from 1.86 to 1.88. Okay, then here is length 161. In fact, it's from 1.88 to 1.86, so that's probably something like an echo or something else. It's actually not the same packet going to the same data. It's some response going back the other way. I'll go back. We'll turn off NSP. I don't want to see DECnet routing data. What I'd like to look is just at DECnet routers. What I notice here, as I just scroll through this, that there's a very large number of DECnet router hellos. End node hellos basically happen every few seconds or so. I think it's every 30 seconds. A DECnet station will broadcast its presence. But normally on a network, you just don't see a large amount of routers on a given network. And what's really curious here is to see a router saying hello, router 2.2 on packet 45, and then down here on packet 51 is another router, station 1.78. Here's another router. Okay, all these are routers checking in. And if we look at the time, the delta time over on the right, you notice these are within tenths of a second from each other. These are not happening every 30 seconds or anything. These are happening pretty frequently. So let's select just DECnet router hellos. We'll use the same technique. I'll put on 3 windows. And We'll select packets that have this value 0B in this value. Notice here that these packets have optional padding in some cases. This byte in DECnet, optional padding length 1, this 81 is a padding byte which may or may not be present. Then the 0B says this is a router hello. Take a look at the next frame. I'm going to press F8, look at frame 53. Frame 53, you'll notice, also has this control format 0B, but it doesn't have a padding byte. So if we want to look at all DECnet routing protocols, we're going to have a pattern that will include both those that do have padding and those that don't have padding. Well, that's pretty easy to do. Let's put up a pattern that includes one or the other. So I'll go to my pattern filters, and again I'll use my cut and paste arrow to copy 0B at offset 10. In this case I'm going to do an OR. I'm going to look at things that recognize DECnet routing where I have padding. I'll go back with F3. I'll pick an example of a packet that does have routing, has padding. That's this one here. He's got 0B at this offset. So what I would do is select this byte, back to my pattern match filter, and down here put, whoops, okay, let's look for this 0B here. At offset 11. So I'm going to look for packets that have 0B at offset 10 or 0B at offset 11. Alternatively, I could look for patterns that have 81, 0B, and I'll type this in manually at offset 10. That's probably a better filter to use. I'll enable that filter. In the future, I might want to give this a name. I might call this router hellos. I could then save this setup. So I could use it in the future to just select router hellos. Now I'll press F3, go back to my display. And here we can see, looking in the summary window, in fact we have pretty much just DECnet router hellos. And they're happening every 1/10 of a second. The first bunch here. And then there's a gap here. Following packet 30, there's about a 7-second gap, and a whole bunch of them come to life again, and then there's another 7-second gap. Pretty typical pattern we see here, where this packet 113 is router 2.2, and here it is up here at packet 45, also station 2.2. And in between, what we're seeing is a pattern of all these routers checking in, starting at packet 45, 51, 52, and so on, and then down here repeating after packet 113. We might look at the relative time in a case like this. Let's see how often this is happening. So I'll turn on relative time. I saw the pattern starting on packet 45. I'll press F2 to mark that. And I've just learned something about DECnet routing. Packet 45 starts, the pattern off, and then there are a series of other stations that check in, and the pattern repeats with station 2.2 about 15 seconds later. And down here at time 29 seconds, here's station 2.2 again, and let's see if we have 45 seconds. Yeah, there's station 2.2, about 45 seconds. So every 15 seconds, all these stations are sending out information about their status. And what we're finding out is that on this network, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 different routers on a network that has only about 24 stations. Well, let's find out what kind of routers those are. We'll look in the detail window for that. I'll press Tab, and what one finds out from the detail window is that this one, station 2.2, is a level 1 router. That is, he's going to route things within his area being area 2, because this station's address is 2.2. So he's going to route things around on level 2, and what he's saying is that he knows of other routers, 2.1 and 2.3, that are also available in area 2. Let's look at the next frame. Press F8. This is area 1, station 78. He's also a level 1 router, and he knows about some other routers. 1.10, 1.77, 1.60, 1.3, 1.86, 1.8. These are also level 1 routers. The next packet is 1.6. He's a level 2 router. He knows about other routers, 2.1, 1.3, and on and on and on. There are dozens of them here. This is a very unusual situation. Typically what you would see in a DECnet would be 1 or 2 level 1 routers on an Ethernet. They would be connected together only in the case of wide area networks, and you would have 1 level 2 router which was then used to connect to some other area. Having more than 1 level 1 router on a network is very strange. Let's turn off router hellos. Here's some information. This packet is level 1 broadcasting all the information it has about the routes that it knows about. What this says is that this station, 1.3, which is in area 1, knows about ID 0 because his cost is not 1023. 1023 is a way of saying that something doesn't exist. Cost 4 says that area 1, station 1 exists, area 1, station 3 exists, area 1, station 5 exists. This station here, 1.88, also knows about station 1, 3, 5, 10. Here's a level 2 routing message that were found. Let's take a look at the detail window of the routing of the level 2 routing message. So this is being sent by the station 1.60, which is a station in area 1, station 60. And what he's saying is that he's in area number 1. The cost to go to area number 1 is 0 because that's area 1. And he says area 2 is 1 hop away. Okay, and it costs 3 units to get to area 2. Now where is area 2? Area 2 is on the same physical Ethernet segment. This network is rather strangely configured. It has both an area 1 and an area 2 on the same Ethernet segment. Not only are they not in remote distant cities or in distant buildings, which is what they normally are designed to do, these happen to be physically on the same Ethernet because we've seen many stations on area 1 and area 2 transmitting data on this Ethernet segment. Not only that, instead of having merely 1 router that would go between these areas or 1 router within an area, the system is configured with virtually dozens of routers. This network needs help. Problems like having too many routers and too many areas can really cause some disastrous situations where packets get stuck in loops, where connections get made and broken, routing tables. You can spend a huge amount of bandwidth just expanding a routing table. This network really differs from Digital's suggestion as to how networks ought to be configured. I'll read you a quote from a DEC publication on DECnet and its architecture. DEC says, DECnet supports area routing on an Ethernet channel. Groups of Ethernet systems may thus be segregated into separate areas. The routing overhead resulting from such a configuration does not make it a cost-effective solution, however. Nodes that would normally communicate directly with one another over the Ethernet cable now have to communicate through intervening level 1 and level 2 routers. So this network needs cleaning up, and we can see that by just observing the pattern of routing information, the high number of router hellos, and the particular router packets that are being sent. For our next example, we'll look at some traces taken from a Novell network system running on Ethernet. And this was actually done here at Network General to collect some examples of how caching works on the Novell system and how you can adjust the parameters. So what I'd like to just show you is what we found when we looked at some data on our own network. I'll look at this file called shared, and shared was the original state of the network. And it's an example of where an individual was logging onto the system, and basically what it would do is to run a program which would cause a menu to appear on the screen. The user would select an application from that menu, and then the program, the system would load that particular application. So what we're going to see is the loading of the menu program. The menu program will read its data files, presumably put it up on the screen for the user, and we then stop capturing. We display that file. This happens to be a case where we're looking at traffic between two different users. So it's a good opportunity to just put us in two-station mode. In this case, we see on the left-hand side of the screen here all the traffic from Harry. Command is from a workstation to a server, and on the right-hand side you see responses from biz1 RRR, responses to this particular data. And let's just take a look at this file, see if we can see anything that we think is usual or unusual with it. First thing here is opening the file called sample.mnu. That in fact is the menu file that was in a public library that contains the selection of application programs that the user can select. The system sent a command over to open that file. Packet number 2 was the response. Notice here that that response took 0.0166 seconds. That's about 17 milliseconds. 17 milliseconds is probably the response time of the hard disk that it had to load it from. That's a reasonable time. If that was 10 times longer, I'd start to worry. In this case, that's saying the system was responding, probably had to do a disk seek, or that's a disk revolution to get that file. And then notice after that, the other packets are happening in milliseconds. A thousandth of a second here, thousandth of a second there, 8/10,000th of a second there, a millisecond here. Those are pretty quick response times as the system exchanges packets. This happens to be a couple of 386 machines talking over a 10 megabit Ethernet. This is the kind of performance you'd expect. Anything slower than that ought to jump out at you. Here's an example, notice here, of a packet that took longer. Again, about 16, 17 milliseconds revolution time on a disk. What was happening? The user was looking for a program, menupars.com, whatever that is, didn't find it. Took a disk revolution to discover that. The program looked again for that same file, didn't find it. Same file, didn't find it. All right, here's a question we'd like to answer. Why are these packets being sent 3 times? Why are we trying to open the same file 3 times in a row? Is that a transmission problem? Is that an application problem? What's going on? Well, we can take a quick look here at the detail window. Open up a detail window. I can see a bit more information about that at first open. Notice when I'm looking at it here, down in the detail window, that the directory handle, this is sort of like the drive letter, that file is being opened on is directory handle number 5, which is generally equivalent to saying that's drive letter A, B, C, D, E. Okay? So it's looking for that file in directory number 5 or drive E. Let's just step down and look at packet 17. Okay, it's looking for it again in directory number 5. So in fact, this system is looking for the same file twice. That's a redundant operation. Here, the 3rd time, it's now looking in directory number 8, whatever that's pointing to. So in fact, there is an opportunity to improve the performance of this application somewhat by looking into presumably the batch file that was executing and seeing which directories it was searching, which directories were in the path to this application, and possibly by tuning that, we could reduce this number of searches from 3 down to 2. What was the next thing that happened? The next thing that happened was, in fact, it tried to open a file called menupars.exe. And you'll see on the next line, in fact, it was opened. This gives us another clue as to what's going on here. This is DOS's rule, that DOS, when you type in the name of a file, it first looks for a COM file with that name through all the directories it has to search, through the path. Then it looks for an exe file with that name. My suggestion on how to, notice then it found it in directory 5. After all, whatever that was pointing to, in fact, it looked there and found the file. One way that this application can be sped up is going to the batch file, editing it, and finding that place where it says MENUPARZ, and changing that to read MENUPARZ.exe. That'll force the Novell system to go out and look for the file.exe, and all this time will be saved. How much time will be saved? In a case like that, we can go up to frame 15, turn on relative time, go back to our display, press F2 to mark it, and read down. And basically what we see here was, in this case, 43 milliseconds was spent on these requests that otherwise could be saved. Not a big deal, perhaps, if hundreds of people are doing it, and it's more typical, in fact, to see in most networks the search going on through many, many, many directories. That's more common. Okay, let's keep looking. It reads the file, opens the file, and here we see something else. Notice it's reading 512 bytes from the file at location 0. Then reads 512 bytes at location 512. Then starts reading through the file 1,000 bytes at a time. This is the executable file. Actually, this is what we'd expect to see on an Ethernet. Novell software tries to use as large a block size as it can, given the network hardware it's working with, for an Ethernet with packets of approximately 1,514 bytes. The largest power of 2 that Novell software can handle is 1024. Unfortunately, one of their options is not to read 1,500 bytes, but it has to read 1024 bytes at a time. One thing to look for is if you see a Novell system that's reading a file and it's less than 1024 bytes, in the case of an Ethernet, it's probably been configured wrong. For some reason, it's decided that the amount of data it can squeeze in a packet is less than 1024 bytes, and it'll end up transmitting twice as many packets through the network. Another thing we can look at here during this section is the amount of the speed of the network, the utilization of it. Let me go, I'll turn off relative time, turn on network utilization. Okay, this network is reading stuff through this Ethernet here at about 20% network utilization. That's good, that's not great. Novell systems can be tuned to, in fact, move data somewhat faster than that, but that's reasonable performance on this particular Ethernet. Okay, there's a lot of time spent here loading that file. Some overlay file gets read. Here the system starts to read the application program, opens a file called syserror.dat, presumably some error message file. Notice here it's reading it 512 bytes at a time, and at random locations in the file. Probably not too much you can do about it because it's not reading sequentially through the file. One would have to look at that application to see what particular packets it's reading, what particular entries it's reading. Now here suddenly we notice that things degenerate. It opens another file, a help file, reads some data from it, and then at this point we see it reading 70 bytes at location 0 from some file. This packet is reading 70 bytes from location 0, the same file. Then reads 70 bytes from location 44 of this file, 70 bytes from location 73 of this file, and on and on and on, reading its way very slowly through this file, reading only 70 bytes at a time, reading overlapping sections of the file. In fact, if we look at network utilization at this point, which I'll turn back on, network utilization here is only 5% of the network, and it's reading very, very small areas of the file. And let's go and find out now what file is it that it seems to be reading, and let's find out why it's not reading that. If this file were cached, we would never see this behavior. For a cached file, what we expect is it would read a 512 byte chunk of the file and then satisfy everything up to byte number 512. Instead of seeing all these reads, it would read just 512 bytes of the file, and then only when it tried to read data elsewhere in the file would it read it. So let's go and find out where that file is, and to do that, what I can do is set up a search in this case, and I've forgotten the file number. The file number is 1B91. I would set up a search, or I would set up we can do another thing. Let's put on a filter for just file opens. That's an interesting thing to do. Perhaps rather than a search, let's find the file open command. Here's a file open command for Novell. I'll turn on a detail window, point to the opcode, the request code for file open, by highlighting that line. Then turn on a filter, pattern match filter, and I'll just copy again. Whoops, didn't want all that data. Let me go back and highlight just the request code. And now I'll copy that request code into my pattern. I'll copy the offset of that into my pattern. I'll hit F3. And now, if I display, notice here I see just the file open commands. It's a quick way of seeing just file opens. Unfortunately, I'm not seeing the file open replies, which is the information I needed. Again, the file that I was looking at is 1B 1B91. I can set up a search to look for 1B91, and I'll capitalize it. Tell the system to search for that in the summary text. Found it at frame 2. And there's the file open request, and here's the file that's being opened. Is sample.menu is being opened, and here's the reply. Let's take a look in the detail window at how that file was being opened. That's the file that apparently is being read just a few bytes at a time. Here's the detail window, and the system is saying open the file. If there's a hidden file or a system file by that name, fine, open it. And it would like to open that file in exclusive or single user mode. It doesn't mind other users writing to the file or reading the file. It doesn't want to write to the file. It just wants to read this file. This is a file that it wants to read. Other people can read it, although it is allowing other people to potentially write to that file. Now, what is this file? This is a file that's in a public library. Everyone in the organization is using the same file. This file was marked in the using the flag command as a shareable read-only file. This file could be shared among multiple users, and it would be a read-only file. Let's look at the next frame. The reply from the system came back and said, fine, I'll open the file sample.menu for you, and this is a shareable file. What does that mean to say it's a shareable file? A shareable file means that you don't have exclusive use of it. Other people may be reading that file, may be writing that file. And if you read the fine print of the Novell manual, in fact, if a file is shareable, caching is disabled. We then went back. Let me show you what the Novell manual has to say about that kind of example, briefly. It says that files flagged shareable can be read by more than one user at a time. This attribute is usually used with the read-only attribute. This is in fact how this file was specified. It was made shareable so that it could be read by more than one user at a time, and it was made read-only to make sure that no one else could write to it. Unfortunately, when the user asks for this file to be opened, the normal default is to, in principle, allow other people to read and write to it. And because of that, the system decided that it couldn't cache the data. Let me load another file. This one is called shared. The only difference was that the flag command was issued. I'm sorry, I want to load the one that says unshared. This is the case where the flag command was issued to make this no longer a shareable file. In this case, the file was opened. The same exact request was made to get exclusive single user use of the file. If we look at the reply, the only difference is the reply came back and said, I'm sorry, this is not a shareable file. That is, you can have it in read-only form, but it is not a shareable file. The implication of that actually is that now only one person at a time can possibly be writing to it, although it happens to be a read-only file. Because it's not a shareable file, no one else might be modifying it at the same time as this user. And now if I go and search for this file, this time the file was opened with a different handle, CD91. Let's search for CD91. Search for CD91. Found it at frame 173. A little context here. Here we were before. It's opening the help file, reads through the help file, and then here it does a read from CD91 of 512 bytes at location 0. And the system comes back and says, well, the file really wasn't even 512 bytes long. It was only 301 bytes long, but I read as many bytes as I could. And this one packet, reading 512 bytes at location 0, followed by the response of 300 bytes, replaces all those packets we saw in the previous example of 70 bytes, 70 bytes, 70 bytes, overlapping each other. I did a tally of what the impact was of that change. To read the file before took a total of 26 packets. After we made that one change to make it a non-shareable file, it took 2 packets. The total amount of network traffic was reduced by almost a factor of 10, and the amount of time to read through that file was reduced from almost 0.2 of a second down to 0.003 of a second. That's a simple, trivial change that was made with one statement to go out and enable caching to be used for that particular file in the case of a Novell network. The next example was taken from a network where the customer was experiencing not just discomfort, but real pain with his Ethernet system. In particular, they were running terminal-oriented sessions during the day using TCP/IP. Other protocols were on the network. And at various times, stations would have to be rebooted. They can no longer communicate with the host. There didn't seem to be any particular pattern as to what was causing it, what time of day it would happen, but basically things would just get hung up. And we took a look with the sniffer to see if we could possibly see what the problem was. So let me load that file. This one here called WinShrink. And the first thing we can do is just take a look and see roughly what was going on in this network. If we look over here, we get some idea. Indeed, TCP/IP is running. Telnet, that is TCP/IP terminal traffic, was happening. Variety of different ports, variety of different stations. Loop protocol, which is some XNS test protocol, was happening. Here's the station sending a carriage return, 0D, we recognize that. Some response is coming back from some file server with some text. Pretty normal stuff. Keep paging around. Here's another page full of traffic that again is TCP/IP and Telnet traffic. Pretty much all the same kind of stuff. We notice a rare couple of packets here on this network. Here is some NSP, some DECnet packets were being transmitted. But on the whole, the network is running TCP/IP and Telnet. To my eye, already there's something very unusual with this summary screen. And what strikes me is that if I just look here at these numbers, window 2796, window 2145, window 777. These are odd. I'll explain to you why I say they're odd. First, a word on what the TCP/IP window is. It's basically a buffer. A station is saying how many characters it's willing to accept from a transmitter into its buffer, and that window shrinks and expands as data is being transmitted and received. So a typical scenario would be, I would start off, I might have a buffer of, say, 1,000 characters. I would receive 50 characters or 100 characters, my buffer will get smaller until I acknowledge that data. When I acknowledge that data, my buffer or my window will grow back up again. So you might see a case where if my buffer started at 1,000 characters and I received 5 or 10, the buffer would shrink by 5 or 10, but then within a matter of literally a fraction of a second, a hundredth of a second, it would bounce back up to 1,000 or whatever I started from. Now, let me give you a picture of what a normal TCP/IP session looks like. To do that, I'm going to turn on a filter and we'll just look at the TCP level of traffic. And what I'll do is load another sample trace from our sample subdirectory of TCP/IP traffic. So this is the TCP/IP.enc example that's in the sample subdirectory. Okay, we have a number of stations transmitting back and forth, and here we can see the window size. Okay, here's a station that has window 512, window 4096, window 512, 4096. Let's go to the end of this trace here. Again, I see just 512, 4096. If we search really hard, okay, here's an example, the only one I happen to find, where the window is not 496 or 512. Here's a case of a window that happens to be 960 bytes, where the window has shrunk slightly from the initial values of 512 or 496. Programmers love powers of 2. Pretty typically, windows start off at values like 512, 1024, 2048, 496, and they will shrink by 1 or 2 or 5 or 50, and then should return back to their initial value of 512 or 496. This is pretty much what you expect then for standard TCP/IP traffic, and occasionally, and it's unusual here, we see very few examples, but this system is a very responsive system. In other systems, you might see the window go down slightly. One of the things to look for is you don't want to see a window which is constantly spending its time near 0. That's a very, very inefficient place to be. If the window is constantly near 0, it means that the transmitter can never transmit traffic. So let's go back now. Let's reload the customer sample data. Wind shrink. And we'll look again at the value of window. And this time we'll focus on a particular station. To help clarify things, let's just look at this very first station and its traffic. The very first station we see here, the address is bridge 00F516. Let's put on an address filter and look at traffic to and from that station. So I'll go turn on a station address filter from bridge F516 and attempt to just see more clearly one station's traffic. Turn on that filter, go back to my display. Now I'll put on two-station mode so I can see traffic going back and forth. Notice here the very first traffic, the very first packet is between this station and in fact this station here, also bridge hardware A6EB. But down here, if you go down, you'll see there is some other traffic going on between this particular bridge station and yet another station. I want to filter that out. So I guess what I'm going to have to do is turn on a filter between F516 and I'm going to select the other half A6EB. So I'll turn on my address match and this time I'll set as the 2 station A6EB. Okay, now when I go back, I can now see the window. between these particular stations. And notice here, now I'm looking at traffic to and from these stations. But in fact, there are several conversations, all happening on different port numbers. 23 is Telnet, but here I have port 5897, 26880, 5897. There actually are two separate stations which are intermixing their communication here. Let's select just one of them. Let's select port 26880. How might I do that? I will go and turn on a detail window. And in my detail window, put the cursor on the source port number, let's say of 5897. And I'll go to my filters. And now I'm going to turn on a pattern match filter. I'll just paste that value into the offset. So that's the destination port. And now the source port I can set as 23, Telnet. Again, just paste that into place. And now notice what I have here is all the traffic between 23 and 587, but I don't have the traffic in the opposite direction. If I want to see the traffic in the opposite direction, I need to go to my pattern match filters and turn on this option that says either offset. Either offset is used so that I can have the source and destination ports reversed on the traffic going in the two directions. Okay, in this case, what I can see happening here is that this window starts off at 1024. On the next transmission, this station sent 80 bytes of traffic, and in fact the window was reduced by 80 from 1024 to 944. That's fine. Now 51 bytes of traffic was sent. The window shrunk by 51. 3 bytes of traffic are sent. The window shrinks by 3. And what we haven't seen happen yet is the window is decreasing. We haven't seen it get larger. And in fact here, this window is 2699. 1 byte of traffic was sent. The window went to 2698 and stayed that way for how long? Well, we can take some idea by using the relative time. I can see, for example, by focusing on this packet where the length was 1, and I'll press F2. This gives me a convenient handle to see roughly how long this time is. And notice here this is 1/10 of a second, 2/10 of a second. These are times in which you would expect the window would come back up. Now in fact, if we look here, what I'm going to do is to turn off reverse direction for a moment. Let's go back to our pattern match filter. Turn off either offset. Display that data. In this display you can see that the data actually, the window size is declining down to 541, and then in fact it does go back up to 1024. It climbs down to 547 and goes back up to 1024. And this particular sample that we're looking at, indeed, the window is not shrinking to 0. It gets small. It goes from 1024 down to roughly half of its size, and then it pops back up. Generally speaking, one sees the window come back up in a matter of milliseconds, hundredths of a second. And we can see that problem happening elsewhere in this trace. We can find examples of where the window has gone to 0. And I'll show you how we can find such an example as follows. Let's turn off our pattern match filter. Find in TCP/IP where the window is. We'll highlight some window value. In this case, it happens to be 784. And now I'm going to make a filter, a pattern match filter. Let's do it down here on match 3. All I really want is the offset of the window, and for pattern I'm going to put in 0. I think it's a word of 0. And I have to remember to go turn off my station address filter. And here we can see all those frames that happen to have window 0. And you'll notice here a whole sequence of them where this station is trying to talk to this station and is acknowledging some data but has window 0. And in fact, what this causes to happen is the other station tries to send its data. We can now filter in on these two stations. And what we'll see is that the communication can proceed because the window is 0. Basically here, what we can see is this station is transmitting a character of length 1, but he's sending it with window 0. And if we looked in more detail at the additional packets, I won't do that right now, well, you won't see responses. And the predicament here is the other station can't respond because this station is sending window 0. And look at the amount of time that's going on here. This station is effectively retransmitting this character over and over again from this period of time. Let's look with our relative time, which we have on. I'll press F2 on this frame 581 here. And what's happening is the station sends it out. Then about a quarter of a second it sends it out. 500th of a second is an act. A quarter of a second later, almost half a second later, 3/4 of a second later, 1 second later, basically this station is stuck attempting to retransmit this one character over and over again. What's happening is that it's transmitting the character and telling the other party to this conversation, by the way, my window is 0, and the other party is respecting it and it can't answer. How would we find out, finally, where the software is that's causing this problem? Looking at the physical address of the station, the fact that this is going through a particular hardware address here, bridge D78B, doesn't tell us the actual station because it may have gone through routers or some kind of server. To solve that, I'll turn on one additional address level change, and I'll turn off the hardware level, turn on the inter-network protocol level. Now if I display it, what I can see is, well, I can't quite see, the station width is not high enough. I'll change the name width from 12 to, say, 15. And now what we see is that the station that is transmitting the window 0 and a character is internetwork address 128.510. And that's the station now we can go to, find out what software is running on it, and find out why it's allowing the window to go to 0, and fix the problem. This was ultimately the cause of the difficulty that was happening here. Only some stations were running the version of software that had this problem. In this method, we could identify all the stations which allowed the window to go to 0, very quickly go to them, and upgrade their software so this problem didn't occur. Every time I look at these traces, You can always discover something else interesting to learn. And for example, in this case, notice the actual internetwork address. It ends with the last digit of 0. Now, that is pretty unusual because, as we were talking about earlier, an address which ends in 0 is supposed to be reserved by the 1988 rules for a broadcast address. In the old days, 0 was used by many people as a legal station address, and 255 was used as a broadcast address. So this is a good example of why there's a lot of confusion on networks in terms of dealing with IP broadcasts and which stations you may and you may not broadcast to, and when you have to rebroadcast data. Obviously, in this network, there are many stations which have internetwork addresses with end in 0. As you've seen, just like Windows 0, we could set up a filter and look for those addresses if that was something we wanted to do fairly easily.